Good morning. How is everybody today? Everybody's working for the weekend. I know I am. I don't think there's any announcements in particular, so we might as well get into things. Any questions or comments before we get started? Yes? Yes, that will happen after class. I have the midterms with me right now. Stay in your seats. I will, I'll be pacing up and down. You know what? Okay. Where's that stick? I need a stick to keep people away from the midterms until the lectures. I took my stick away. It's okay. I'll just have to use my bare fists. All right. Yeah, I have the midterms. We'll distribute them after class. Any other questions? The long-awaited midterm results. Okay. So it goes. So we were talking about topological sort. We were talking about how the vertex, in order to come up with a topological sort of a graph, all you need to do is perform a series of depth first searches over said data structure, and that, if you do that, record which node you have visited once those depth first searches are terminating. Reverse that list, you will end up with a topological sort as if by magic. So I did an example on the board, but it's a little bit of a complicated thing, so perhaps it would be useful to see it again. Yeah? Who wants to see it twice? See it again. Yeah, okay. I think the eyes have it. So, one extremely necessary precondition for the topological sort, this is very light chalk. Wow. Geez, what is it even made of? They made chalk out of clouds. Sorry, I'm just like in an easily distractible mood today because probably I didn't get a lot of sleep because the baby was keeping us up all night. But anyway, so with topological sort, the number one very most important precondition is that the directed graph be acyclic. What does it mean to be acyclic again? And does not contain cycles, yes. So, still works as chalk though. Man, it's like tiny. No, I can't stand that. I have to use my proper chalk. It's probably like diet chalk. It's like how Diet Coke is like worse than Coke, you know? Yeah, there we go. Proper chalk, mined from the earth, not reconstructed. Like, honestly, I want you guys, when you're getting your tests, to feel the difference between these two. Anyway, let's make it slightly larger. All right, so. I believe that to be acyclic. Do I have the concurrence of the class? Good. So, one piece that I skipped last time, which I think I'll do this time, is I didn't do the adjacency array, so let's do the adjacency array, shall we? So we've got 0 through 6. 0 goes 3 and 1. 1 goes to 3. 2 goes to 1 and 3. 3 goes to 5. 4 goes to 0 and 6. 5 goes to, it's nothing. That'll be my symbol for null. And 6 goes to 0. Ta-ra. In addition, let's just do out a marked array at the same time. And let's keep our reverse post order list at the bottom. All right? We'll start over here and build it up this way because we're building it reverse. So, since we have to go through all of these with depth first search, no reason not to start with the first one, right? So we will begin by calling depth first search on 0. Here we are. So we're currently here. We take a look and so with our depth first search, we are performing, what order do we do the nodes in for depth first search? Come on. What order do we go through the nodes in for depth first search? Yes? The order as they appear in the adjacency matrix. Very good. I mean, it is not technically a matrix. I was wrong. It's the adjacency list. But anyway, so that means we're calling depth first search. You know what? I'm just going to call it D, capital D. It's faster to write. D at 3 is the first one. If we imagine the stack, right? We currently have 3 and 1 on the stack. We're processing 3. To process 3, we look up what it has. 3 has 5. So we pop 5 onto the stack, calling depth first search on 5. 5 finds nothing else, right? So 5 terminates. 5 terminates. I'm using this symbol for a lot today. Therefore, we put 5 in our reverse post order list. And as the more astute of you perhaps have already noticed that 5 was going to be at the end of that list no matter, our intuitions about what comes last in a topological sort of this graph, this is the last element. All elements will flow to this one, right? So we're already on a good track, right? So 5 is processed, so we don't have to worry about it anymore. I haven't been marking things. So we have visited 0, we have visited 3, and we have visited 5. So we take a look at 3. 3 has nothing else that it's going to except 5. Pop that off the stack, terminate. Add that to the front of the reverse post order list. Now we process 1. Taking a look at 1, we can see it has only 3. Well, first of all, we check it off. 3 is the only node that 1 points to. We can see that it's already checked off, so we don't have to visit it again. So it goes. 1 is then terminated. We put it there. And 0 has no more elements to process, so we close that off. And 0 gets added to the reverse post order list. So far, so good. We then proceed to the next item in the adjacency, in the list of nodes that has not been marked. So in this case, that would be 2. So our starting point is now 2. We can see where this is going very quickly because 2 is already only pointing to marked nodes. So, nevertheless though, we follow the procedure. DFS2, no unmarked nodes yet left to process, so we terminate 2. 2 gets added to the reverse post order list and checked off. We then proceed to the next item that's not checked off, which is in this case 4. So we now open up depth first search on 4. We take a look at the adjacency matrix and find that 4 points to 0 and 6. 0 has already been marked off, so we don't have to process it. 6, however, has not. So our next call is to 6. 6 again, and we check off 4. 6 has not yet, 6 has no unprocessed children, so we check her off, say this thing is now terminated, add it to the reverse post order list, boom doom, and then terminate 4 because it has no additional children. There we go. Add that to the reverse post order list. Good, good, good. The only thing left to demonstrate is that that is in fact a valid topological sort, which we're technically done here, but I wanna like prove to you that this is in fact a topological sort. So I'm going to just do that quickly. If we take the nodes and we line them up. Right? So looking at 4, 4 has 0 and 6. 6, 0. 6 has 0 as well. 2 has 1 and 3. 1, 3. 0 has 1 and 3 as well. 1, 3. 1 has 3. 3 has 5, and 5 has nothing. Ta-da! So it's kind of cool, right? Yes? Yes. Yeah, it's first in, first out. Wait, no, last in, first out. Yes, it's a stack. Stack, 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 yes.
So for example, because you called that first search on the first list in the adjacency matrix. So you're going to add some sort of adjacency list.
Yeah.
So when you call 0, you would add 1 and then add 3.
Yeah, so I was kind of just keeping this to, because I think it's a little bit confusing, like the fact that depth first search is like embedded in the call system rather than being able to explicitly see the numbers build and contract. But in this example, I guess I wasn't as fastidious about keeping things on the stack as I should have been. But yes, just to run through the procedure quickly again. 0 gets put on first. Then we put things on the stack. 1, 3, right? Those are the 2 elements. You'll notice that the order in which they're getting put on the stack is actually the reverse of the order that they appear in the adjacency matrix because we want to process the first one first, right? and then 3 finds 5, and then 5 finds nothing, so we process that, 1's got nothing, and 0, and that's how the stack works. If this were breadth first search, we would eat from the bottom rather than from the top, right? Cool. Any other questions? Oh, is there someone with a question? Oh, right, sorry. Right. Next time, shout at me. What's the point of doing this? Oh, there's my stick. Wonderful. So the point of a topological sort, were you here last class? Yeah. So you remember when I showed you how this had actual application to my thesis work? Yeah. So, well, it has, in at least my case, application to my actual thesis work. So that is some application. But in general, right, you have to think about what the graph itself represents, right? So think about it this way, right? Let's imagine that each of your nodes is a process, right? And each of the edges is a dependency relationship between processes. You could think of it, this process requires the output of this process, that process, and the other process, right? So like, if we're making a, oh, this is the bad chalk, oh well. If we're making a cheeseburger, oh, it's so terrible, right? Just makes me uncomfortable, right? With the cheese and the buns, right? Making the cheeseburger is dependent on making the bun, making the meat, and making the cheese, right? So if your question is, what order do I need to perform these tasks in order to have a cheeseburger at the end without having to, without starting processes that need to be interrupted because they're missing the ingredients? Then topological sort will show you that. Does that make sense? Obviously, examples get more complicated than cheeseburgers, right? You can kind of think of the entire economy in this way. Like, how many parts do you think goes into a car, right? And all those parts have to be finished before they are assembled into more complicated pieces and sent further down the, chain of manufacturing until you eventually end up with the finished product. So, but of course, the thing about an actual economy is that all of that would be parallelized, right? Different things would be made in different plants. If you had one universal plant that did everything, this is the order in which that plant would have to do these operations to produce the result. In computing, this is actually the situation that you're in, because computing resources tend to be very limited, and most of the time, for simplicity, we will model a computer system as being able to process one task at a time, right? Despite the fact that parallelism is an increasingly important role in computing, it's sufficiently complicated that you probably won't study it in depth till like 3rd or 4th year, right? So, yeah. Does that make sense? Cool. Any other questions? So I'm going to assume that my example there is better than the example that's in the slide, so I'm just going to skip it. So, why does topological sort work? The last vertex in reverse post order, i.e. first vertex in post order, has an out degree of 0. Second last vertex in a reverse post order can only point to the first vertex, etc., etc., you can construct the argument inductively from there. A digraph has a topological order if and only if it is a directed acyclic graph. If, for example, there was another arrow here, topological sort would be meaningless. We would introduce, like, there would be no possible solution because you'd have, an arrow going up this way, and it's impossible to resolve that. So we will leave it off. Yes?
Sorry, to get a post order result. So basically, we will change the data structure of the stack to Q for that cases.
I would say it's not correct to think of the reverse post order as either a stack or a queue, because we never intend to remove items from it. So it doesn't matter what order we do something we never intend to do, right? So the reverse post order list, the reason I'm calling it a list is because adding to the head of a list is a constant time operation, right? So it makes sense. It makes sense to use a list for this as opposed to an array, right? Just from a runtime perspective. But no, all this is doing is you keep a list, and every time one of these functions terminate, you take that vertex number and you put it at the head of the list.
Okay, so it's a linked list to put it.
Yeah, this is just a regular linked list.
Okay.
Yeah. I mean, again, you can use many data structures for many purposes. An array you could also use, but a linked list would be efficient. Yes? Yes, yeah. So the question is, could you still run the algorithm on a graph that did contain a cycle? And yes, you could still run this algorithm on a graph that contained a cycle. But the required precondition to the algorithm is that there are no cycles. The expected post condition for the algorithm is that this is a topological sort, right? And topological sort meaning anything higher in this linear arrangement will only point to things that are below it, right? So if the input condition does not hold, the output condition will not hold. Garbage in, garbage out. Thank you. Any other questions? So let's talk about running time. A digraph has a topological order if and only if it is a directed acyclic graph, as has been read. We've leaned on that point quite a bit. With depth first search, we can produce a topological sort in a running time proportional to the number of vertices plus the number of edges. If you remember, back to when we were discussing depth first search, the running time of depth first search itself was proportional to the number of vertexes plus the number of edges, or the cardinality of both sets. So, given that, to produce a topological sort, all we need do is add maybe 2 or 3 lines of code to our regular depth first search algorithm. It is, straightforward. It should be relatively straightforward that our runtime has not changed. Make sense? Good. So let's now talk about a different problem. And now for something completely different. So we now know that it actually does matter whether or not your graph contains cycles, right? If it contains cycles, you are on a different planet than if it does not contain cycles. The same algorithms will not necessarily apply. Therefore, it is useful to be able to tell if a graph has cycles. It is not always obvious, right? Let me see if there's a good illustration of that in the coming slides. There's a good example of that in the textbook. It's like a 20 by 20 field of nodes with each one pointing one way or another, and it's like, does this contain a cycle? And it's like, you certainly can't figure that out by examination easily like you can in these examples. So, given that, it's not possible to know, it's like many things, this property can't just be intuited from the data structure. Because in the case of graphs, we are not maintaining the data structure in such a way as to exclude the possibility of cycles in graphs, right? Cycles can actually be useful in graphs. So, the recursive stack call maintained by the system during depth-first search represents the current directed path under consideration. By maintaining a vertex indexed Boolean array on stack, we can keep track of the elements in this call stack. If we ever find a directed edge V to W to a vertex W that is on the stack, we have found a cycle, since the stack is evidence of a directed path from W to V, and the edge V to W completes the cycle. So, in essence, so what's the purpose of keeping the on-stack array, which is just an array of Booleans, versus just searching the stack, which is something that we could, in theory, also do? What's the advantage? Come on, you've been taking this course long enough to know this. You answer a lot of questions. I want to see if someone else has got it. What's the advantage of direct array access versus a linear search? Yes? Constant lookup time, right. You guys better shape up for the exam. So, if we keep a separate array which keeps track of whether something's on the stack or not, it adds at most 2 assignment operations to the entirety of the algorithm, right? It means that we no longer have to search through the stack itself to find if something is on the stack. Searching through the stack is, of course, an operation that will take an amount of time proportional to the size of the stack, right? And we simply need to know whether it is in the stack or not. So, that is the advantage of keeping an on-stack array. Make sense? Good, good. Any questions? You can see that this is already, and again, just a slight minor modification of our existing algorithm to turn it into something else that does something else. So, basically, you introduce one additional test. When you hit, when you're examining the children of any particular node, you also check the on-stack array to see if it's been put on the stack previously. If it has, you have a cycle. If it has not, then you proceed as normal. If the purpose of the algorithm is to detect all of this, to detect the whether or not the thing contains cycles, this is sufficient. If you want to know what those cycles actually are, That's a different question, right? The purpose of this is just to produce a Boolean test to see if cycles are in there or not. It won't give you the cycles themselves, although it will tell you what cluster they're in. Right? Make sense? Good. It's certainly possible to determine what the cycle actually is, by taking the node that, well, one way you can do it is you can take the node that you've returned to and then, do a breadth first search looking for itself or something like that, but yes?
I see the on-stack array is pretty much duplicate as the marked array. What's the purpose to have this two in the same place?
Excellent question. So the question is, why keep both of these, as marked seems to be doing the same thing that, that on-stack does? Marked is preserved through subsequent calls to depth first search at the top level. So marked is preserved through that, whereas the on-stack is not. So on-stack is cleared when the stack is cleared, right? And, on-stack is cleared as things are removed from the stack, right? So in this, again, I have a problem with the text using like two specific examples, On-stack doesn't really show what it's doing until you're in the middle of the algorithm, right? At this point in the algorithm, they've only processed 4 elements, right? And they haven't, nothing yet has been popped from the stack according to this trace, right? We haven't closed off any of these yet. So when we close these off, this guy has ones removed, but this one keeps them. Make sense? Yeah, good. Good questions today. All right, good. So, we will now talk about strongly connected components. So, definition. Vertices V and W are strongly connected if there is both a directed path from V to W and a directed path from W to V. So, strongly connected components. We can see that in the cluster containing 0, 2, 3, 4, and 5, right? Any one of those nodes is accessible, is part of the cycle, or can be part of the cycle, right? So you can go, 0, 5, 4, 3, 2, 0, right? That's a cycle, and it contains every node in that cluster. It is possible to have these things overlap as well. You can already think of overlapping, this big one overlaps with a sub-cycle 3, 5, 4, right? As well, but anyway. 6, 8 is one, obviously. 9, 10, 11, 12 is one in this graph. Very good. Give me a second. So, key properties. Strong connectivity is an equivalence relation. V is strongly connected to V, so that's reflexivity. 1 is strongly connected to itself, as is 7, even if it's not strongly connected to anything else. If V is strongly connected to W, then W is strongly connected to V. So that's what math property is that?
Symmetry.
Symmetry, symmetricality, yes. And if V is strongly connected to W and W to X, then B is strongly connected to X. What is that mathematical property? Transitivity. Good. Definition. A strong component is a maximal subset of strongly connected vertices. So, the component itself, right, is the maximal subset, right? So there are actually this one makes a better example, right? So 9, 11, 12 is a cycle. 9, 10, 12 is also a cycle, right? There are two subcycles inside of that strongly connected component. But the strongly connected component itself is considered to be the maximal subset of that group of all the cycles engaged in by that group of nodes. So, you could go 9, 11, 12, 9, 10, 12. So it's like a double cycle that crisscrosses on itself, right? Make sense? You had a question?
Based on the first definition above, can we say that if we had an undirected graph, then all pair vertices are strongly connected?
Yes. So the question is, based on this definition, are all nodes in a undirected graph strongly connected? Since we are modeling undirected graphs as directed graphs where all edges are bidirectional, then in every case in which you have an edge, you would be in a case like 6 and 8 in this diagram. So yes, absolutely. Any other questions? Okay. So, this is kind of a, I hope everybody could have gotten this without a slide on it, but there is a difference between strongly connected components and connected components. A connected component, let us remind ourselves, is simply are there edges between the elements of this, what we're considering this grouping of nodes, right? In order for it to be a connected component, every node has to be connected to every other node. If it's strongly connected, then you also have to be able to loop around inside there. Make sense? Yes. So, in the case of connected components, we keep an ID array where we keep identification numbers associated with each of the components in the same manner that we were doing union find way back at the beginning of the course, right? So, finding whether or not two elements are connected is a simple equality comparison on two lookups to the ID array, right? So, in the case of strong connectivity, we can produce a similar ID array that contains, which maps each vertex to an ID number for the strong component that it is a member of. So, in the same manner, we can produce a constant time algorithm for looking up whether or not these elements are strongly connected or not. Make sense? Good. So, does anybody have any idea how we might be able to write an algorithm to populate this array? How do we find out which components or which vertices are strongly connected to each other? Think about the algorithms that we've talked about most recently. Think about slight modifications of them. Is it just a Friday? Is that the problem? Everybody's just, ugh. Or everybody's just here to get their tests? No ideas whatsoever? Yes?
Is that just using the depth first search for each arguments and have a set?
Mm-hmm. So, remember the on stack? Right? So, this thing's going to have a maximal extent, right? The items that are on stack during a depth first search inside of one connected component, that's going to like basically once we hit a cycle, right? Then we can use that information to determine where the strongly connected components are. So let's see how they're running. So, the Kosaraju-Sharir algorithm. Simple but mysterious algorithm for computing strong connected components in a graph. So this is how we're doing it. We run the depth first search on the graph reversed. All right. So we take the graph and we reverse every edge in it, right? And then we compute the reverse post order. Then we run depth first search on the graph, considering the vertices in reverse post order. So we generate a reverse post order on the reverse graph. Then we take that ordering, which is a topological sort, and we put the graph back into its forward direction. And we run depth first search considering the vertices in that order. So, phase 1, run depth first search on the reverse of the graph to compute the reverse post order. Phase 2, run depth first search on the graph considering vertex in the order given by the first search. So, I don't think we can do the example in 2 minutes. So, I think that'll be it.